my name is Angela Lynn, and today I'll be presenting on Lab 4 regarding oscillations. So the purpose of this lab was to track the motion of a mass oscillating on a spring and to create a model to predict that motion. And then with the model, we'll compare it to the observed results. The main result of this experiment was that the model was effective in predicting motion in the x direction, but not as accurate for the y direction motion. And this is likely due to the exclusion of drag and other forces and energies like thermal and chemical energies. Here are a few important formulas. One of the formula related to this lab is the work energy principle, whereby delta E system equals work done by the surroundings. Here we look at the mass, spring, and earth as a system, with the surroundings being nothing. So therefore, the formula is delta K plus delta potential energy of gravity plus the delta potential energy of the spring equals W, which will then equal 0 because the surroundings is nothing. We also need the respective formulas for K, the potential energies of the gravitational and spring force and their components here. And also we will need the update position and update velocity formulas to track and update motion of the mass as it oscillates on a string. First, in Tracker, I imported the provided video and calibrated the distance from the spring's fixed end to the mass's center, and that is 0.7 meters. And I then set the origin at the spring's end. Since the object is initially at rest before release, its initial velocity is 0 meters per second. And I then, after tracking the mass, I extracted the initial position, which is shown here. In the computational model, I edited these lines for the ball's mass, which is 0.402 kilograms, as well as the initial conditions of position and velocity. To get delta T, I found out how many seconds were per frame, which was 0.0905. I also edited these lines for the gravitational constant, as well as the spring constant and the relaxed length. And I also edited these lines to find L, L hat, and S as part of the formula for the spring force. And these lines here correlate to the respective formulas of these components. Another part of the code was to track the energies. So I edited lines for F grav, F spring to their respective formulas, with F net being the sum. I also edited the update position and velocity lines to their respective formulas. For the delta components, I subtracted the component that was the initial value stored in the section under initial energies. This is the computational model. Running the computational model, we see that the change in energy, which is the orange line, is 0 as predicted. This is because we see that the gravitational and the spring energies do oscillate, signaling that energy is being transferred between those states and to translational kinetic energy. So there is actually no gain or loss of energy, but a conservation of energy, which is 0. So the observed Y motion deviated more from model than the Y position motion, and this is possibly due to not accounting for forces like drag. Another potential source of error would be through the inaccurate tracking through Tracker. Here we see that the X motion from the experiment aligned more closely to the model, whereas the Y position motion did not follow as closely. And there are some gaps that we see here. In all, we do see that the energy principle is satisfied because energy remained 0 throughout the oscillations as energy was transferred from kinetic to the different potential energies of gravitational and spring force. To calculate the oscillation periods for the X and Y motion, we have to look at the time between two troughs. For the X position, that was 1.619, and Y position 1.424. So the Y position had a shorter oscillation period, possibly due to not accounting for drag forces or through inaccurate tracking through Tracker, as stated before, affecting calculations of the gravitational and spring potential energy.